Hi guys, and welcome to another video tutorial in organic chemistry. Today's topic is going to be intermolecular forces. So from general chemistry, there are essentially three different types of what are known as intermolecular forces, or IMFs for short. So intermolecular forces are the forces of attraction or repulsion that exist between molecules of a given substance or combination of substances. So there are three general intermolecular forces. The first one is known as a London dispersion force, otherwise known as van der Waals forces as well. That is a different name that is also used. The second is known as a dipole-dipole. And the third is known as hydrogen bonding. So the types of molecules that exhibit these different types of intermolecular forces. For the first one, London dispersion forces are primarily predominant in molecules that are non-polar. So all non-polar molecules exhibit London dispersion forces only. For dipole-dipole, the types of molecules that exhibit this force are polar molecules. And the third, hydrogen bonding. To me, it's a special type of dipole-dipole. So these are polar molecules as well. But the difference is that there's going to be a very special, unique feature. So these polar molecules, they must contain either an oxygen-hydrogen bond, or OH, or a nitrogen-hydrogen bond. And we're going to see examples of these and how these work. London dispersion forces, we're just going to focus on much simpler molecules, such as the hydrogen molecule and maybe a chlorine molecule. So in the hydrogen molecule, we obviously have two hydrogen atoms, which are connected by a single covalent bond as such. Now, because we have two elements that are exactly the same, the electronegativity difference is 0, and therefore the molecule is considered to be nonpolar. So when it comes to bonding, each hydrogen has a 1s orbital that is used for bonding to the other hydrogen and vice versa. So pictorially, if we take our two 1s orbitals as such and we combine them together to make a what is known as a molecular orbital, the representation of what the electron clouds look like is something of a peanut shape, but we're going to just make it something much simpler, something that sort of looks like a potato. And so the nucleus of each hydrogen is about here, like this. And so this oval shape here that I've drawn is supposed to represent the smearing of the electrons, or the electron cloud. So in hydrogen molecules, every single hydrogen molecule looks exactly like this picture that I've drawn. Now, because the molecule is nonpolar, there are no positive or negative charges anywhere on the molecule, or partial positive or negative charges. what this means is that the electron cloud is spread evenly throughout the entire molecule. So even though the electrons are spread out evenly, this doesn't mean that the electrons stay in one place. Because as we know, electrons tend to travel in circles. So obviously each hydrogen has its own single electron, and these electrons are whizzing around the entire molecule. So at any given instant, even though electrons like to be spread apart as far away from each other, they are attracted to the nucleus of the atoms. And so there are instances in which you may be able to find the electrons, rather than separate on two ends of the molecule, you might find them very close to each other on one side of the molecule, but not on the other. And this happens simply due to the fact that the electrons are always constantly in motion. So at any given instant, there may be a point where the electrons are sort of concentrated on one part of the molecule, but not on the other. Now, when this happens, because you have electron density, or electrons smeared on one side more than the other, this causes there to be an excess amount of negative electrical charge on one side and a vacancy of negative charge on the other. And there's a way that we depict this in chemistry by using this Greek letter delta. This Greek letter delta stands for partial. If you've taken calculus, you've known that this is what this means. And if we put a negative or a positive symbol next to this delta, it literally reads as partial negative or partial positive. So when this happens, we're going to redraw this, and we're just going to indicate the partial negativity and partial positivity. If the electrons are on one side of the molecule, this part of the molecule, or this end of the molecule, is going to become partially negative. It's only partial because it isn't a full negative charge. It simply means that the electrons are more concentrated in this area of the molecule. And conversely, on the other side, we're going to need to have a partial positive charge, because all we have on this side is the nucleus, which contains the proton, which is positively charged. So there's an absence of negative charge on one end and a more than enough negative charge on the other end. And so this happens with one individual molecule, and these partial negative and positive charges, they exist for fractions of seconds. As soon as the electrons come very close to each other and they sense each other's negative charges, they will repel and the electron will shoot over onto the other side. So even though these partial negative and positive charges are existing for only fractions of seconds, what happens is when this negative charge builds on one part of the molecule and the positive on the other, this causes there to be what is known as an induction effect on another molecule. So because there's a concentration of negative charge on this molecule here in red, that causes there to be a disruption in the electron cloud of another molecule. And since opposites attract, the partial negative charge that's written here is going to attract the nucleus of the atom on this side with this dot that I've represented, and the electrons are going to shoot over to the other side in order to avoid the partial negative charge that's built up here. So that means that this side is going to become partially positive, and the other side is going to become partially negative, just like our first molecule. And as you can imagine, this can continue down the chain of hundreds and thousands and millions of molecules. And so these short moments in where the molecules have partial negative and partial positive charges, and this then causes there to exist partial negative and partial positive charges on other molecules, is the mechanism by which the London dispersion force exists. And so this is why hydrogen at certain temperatures can eventually become a liquid and then eventually also a solid. Chlorine is another molecule that is nonpolar, and obviously we draw chlorine the same way that we draw hydrogen. It's a single covalent bond with electrons as lone pairs. So the major difference between hydrogen and chlorine just has to do with size. So the chlorine molecule is much larger than the hydrogen molecule, and so its electron cloud for the entire molecule is going to be much larger. So the same effect occurs with chlorine as does with hydrogen. The electrons are constantly whizzing around, and this causes there to be partial negative and partial positive charges. The main difference is that with molecules that are much larger, like chlorine compared to hydrogen, the amount of partial negative and partial positive charges is much larger. Not only because the molecule or the atoms themselves are much larger, and so the electrons spread out a lot more over a much larger area here. So the amount of negative charge that can exist in this small area is much larger because of its area. But also because you have many more electrons going around. Right? So not only is it the electrons from the bond, but it's also these lone pairs that exist on the chlorine that are always constantly in motion. And so with larger molecules, you're going to have much larger partial negative and partial positive charges occurring. And because the charges are much larger, what that then means is that the attractions between these partial positive and partial negative ends is also much stronger. And this then goes into predicting the physical properties of hydrogen versus chlorine in terms of boiling points, melting points, density, and many other physical properties. So we saw how nonpolar molecules will always have London dispersion forces. For polar molecules, we're going to have dipole-dipole interactions. One of the simplest molecules we can do is hydrogen chloride, which is a simple linear molecule of just two atoms. And you can obviously extend this to more complicated molecules that are more than two atoms and have more complicated shapes, but the basic principle is still going to be the same. If a molecule ends up becoming polar due to its geometry and the atoms involved, then the same principles that we do here are going to apply to that particular molecule. So I'll show you another example after HCl. So with hydrogen chloride, so we know that the chlorine atom is more electronegative, and so to represent the bond polarity, we're going to draw an arrow that points from hydrogen to chlorine. Now, because the molecule is linear and we only have one arrow, and this single arrow points in a single direction, this bond polarity is also the molecular polarity. So what this is indicating is that the chlorine is pulling electrons away from the hydrogen and to itself from the bond. So chlorine, being more electronegative, has a stronger pull on the electrons that are in the bond than does hydrogen. So what this means is that just like with our instantaneous dipole, we're going to have partial negative and partial positive charges. The main difference is that these partial negatives and partial positive charges that exist in HCl and all polar molecules, these are referred to as permanent dipoles, because these dipoles always exist regardless of any London dispersion forces that might exist. These dipoles are always permanently here. The chlorine is always constantly pulling the electrons away from our hydrogen atom. So as you can imagine, if we have a multitude of hydrogen chlorine molecules next to each other like this, or even randomly dispersed in this way, because these are all hydrogen chlorine molecules, they are all going to have the same polarities. So all the hydrogens are going to be partially positive, and all the chlorines are going to be partially negative. And so, since opposites attract, the partial negative charges of our chlorines are going to attract the partial positive charges of our hydrogen, and vice versa. And so these attractions are really strong, again, because the dipoles are permanent. Unlike a London dispersion force, where the dipole only exists for a fraction of time, and therefore the attraction only exists for a fraction of time, here, because the dipoles are permanent, the attractions are always there. So they're always present. And so because they're always present, the attractions are that much stronger. So this is an example of a dipole-dipole force that exists between polar molecules. Now the same can be done with, let's say, something a bit more complicated. So this is the molecule or the structure for acetone, which is found in most common nail polish removers. So oxygen is more electronegative than carbon, and so we're going to have an arrow that points from carbon to oxygen. I should have drawn the carbon atom that is in here. I'm sort of jumping ahead a little. So the other bonds between carbons and carbons are nonpolar, and the bonds between carbon and hydrogens are also nonpolar. And so we only have one dipole or one bond polarity arrow, the same as HCl. And so again, with acetone, we're going to have a oxygen, which is partially negative. If we draw in our partial negative and partial positive charges, we're going to draw just two of these molecules here. Okay, and so our oxygens are going to be partially negative, and the carbons that they are attached to are going to be partially positive. And so just like with HCl, the attraction between the positive end of, or the positive part of one molecule and the negative part of the other is going to show the attraction between those two parts of the molecule. And the last type of intermolecular force, which is hydrogen bonding, as I said, is a sort of just special type of dipole-dipole. So the simplest example of hydrogen bonding is in the molecule of water, which we already saw has a molecular dipole that points straight through the middle of the water molecule. And so to represent the partial negative and partial positive charges, we're going to show that the oxygen is partially negative, since that is the partial negative part of the molecule, because that's the direction in which our molecular dipole is pointing. And then our hydrogens are both going to be partially positive. And so we're going to do this with another molecule of water again, just drawn here. And I'm drawing it purposely this way so that we'll see how the partial negatives and partial positives attract. And so because this molecule of water has oxygen-hydrogen bonds, rather than calling it a dipole-dipole force, what we do is we call it a hydrogen bonding force, or just hydrogen bonding for simplicity. And the reason for that is simply because oxygen and nitrogen are the two most electronegative elements in the periodic table, because they are furthest over to the right. And so because they are the most electronegative, whenever molecules that involve oxygen and hydrogen, or nitrogen and hydrogen, they're going to have really, really strong or really high partial negative and high partial positive portions. And so because the partial negative and partial positive portions of the molecules are really high, the attractions between the molecules are that much more stronger. And so this leads to physical properties that, again, like physical melting point and boiling points for something like water, is very unique. So for water, we know that the boiling point is 100 degrees Celsius. If you compare this to the other hydrogen molecules or hydrogen compounds that are formed for the other elements in the same group, what you would notice is that the water molecule, even though it is the lightest, because oxygen is the least heavy element of the four here, the water actually has the highest boiling point compared to the other three compounds that are formed. And all these compounds have the exact same geometry. They're all bent. The difference being is that these last three here only exhibit dipole-dipole rather than hydrogen bonding interactions. And so dipole-dipole forces are weaker than hydrogen bonding. So we see that this oxygen-hydrogen bond is very important when it comes to determining intermolecular forces. Some other common things that you might see with hydrogen bonding is, so this can be obviously between water molecules. If we have ammonia and water, so ammonia looks like this, and of course water looks like we just drew it. Here we can also have hydrogen bonding. So anytime there are oxygen-hydrogen bonds, as well as nitrogen-hydrogen bonds, we can have hydrogen bonding. So we can have hydrogen bonding between ammonia and water, water with itself, or ammonia with itself. One very common mistake that students make is if we take water and we take acetone, which we just drew in the previous part. So we deduce that acetone is polar, and this oxygen here is partially negative, and the oxygen for water is partially negative, as well as the carbon being partially positive in acetone and hydrogen in water. So here there's an example of two molecules that are polar, but we wouldn't say that the attraction or the intermolecular force is hydrogen bonding. And the reason for this is because even though this oxygen is partially negative, the hydrogens are not attached or bonded to that oxygen. The hydrogens are attached to a carbon atom. And so for this case, in the case of water with acetone, the intermolecular force that exists between these two is only dipole-dipole. Okay, in order to be considered hydrogen bonding, both molecules must have either a nitrogen-hydrogen or an oxygen-hydrogen bond. If one of the molecules does not have an oxygen-hydrogen or nitrogen-hydrogen bond, then you cannot consider the attraction between those two molecules to be hydrogen bonding, as is the case with water and acetone. Alright, so this summarizes the intermolecular forces. Hit that like and subscribe button for more videos like this in organic chemistry.